So let's begin. This is the last class of the second epoch of the course. At least, although there's a slight chance the epoch bleeds over into next week, but I think we can get through all of chapter 2 today. So today we'll do a little more in 2.4 and spend a bunch of time on 2.5. I think today will be a lot of exercises, things to try out and then talk about, rather than me talking about and then having you do things. Since a lot of these things, it's just so much more valuable if you think about them and puzzle over them first. Lots of homework help coming up. Teresa, 7 to 8. Corey, are you 11 to noon tomorrow?
Yeah.
Okay.
He's doing 4 to 5:30 today.
That seems plausible.
Yeah.
5:30. I have a meeting tomorrow from 1 to 2. The meeting may run a little bit over. It's down in Turrets. So I'll be up at take a break as soon as I can sort of extract myself from that meeting and the post-meeting meeting, if any happens. And I can stick around for a while. I think I've got a meeting at 3:30. So if there are tons of people there, there might be some differential equation students too. I shouldn't be too pressed for time. A lot of stuff is going on this weekend. Maybe you know about some of that. The board meeting, the quarterly board meeting is happening. With the exception of a few executive session portions of meetings, all of those meetings are open. And so you can, if you're curious, you want to talk about fences or anything else for a while, there will be lots of settings in which you could do that. And they'll be going to some events on campus, and if you see them, they always love talking to students. It's also family and friend and alumni weekend. It's just sort of, I think, isn't it? Yeah. Okay, good. So it's like everybody's going to be on campus. So again, say hi to them and be nice to them, and then, because then nobody's going to come to campus like until May. Okay, it's probably not that bad. But anyway, the Columbus Day weekend always, for me, it sort of always marks the beginning of the quiet season, the contemplative season here, the easy parking downtown season. Anyway, a lot of alums will be on campus, families, friends. There are a ton of events. The weather's supposed to be nice, so be sure to do some of that. All right, so as I've written on the board many times, this is what we've been doing. All right, so chapter 1, it's like a new thing every half hour. This chapter is hopefully seeming repetitive, not in a bad way, repetitive, I hope, but like that we're kind of doing the same thing again and again in slightly different ways. So we've been talking about the derivative. The derivative is the rate of change of a function. So the derivative of a function is this limit thing, these difference quotients. And once you've got your hands on these, you could evaluate it on a calculator or try to do some algebra and see if you can get rid of this potentially explosive h. What this means in words is it's the average change from x to x plus h, and you let h get closer and closer to 0, and you see what happens. That's just the words for what that means. What you're left with is the instantaneous rate of change, how fast the function is changing at that particular x value. Geometrically, it's the slope. The slope changes all the time, so you'll get different answers for different x's most of the time. So it's a slope of this line, the line tangent at that point. All of this concept and all of this procedure is abbreviated by this tiny little apostrophe. And then we learned last time, although we didn't talk about it too much, we'll say a little bit more about it today, that an alternative notion is this. This is a Leibniz notation. And I like to think of this as it's a little bit of y divided by a little bit of x. So d for like delta change in, but it's a small d, so it's a little change in, an itty-bitty change in. Sometimes they're called infinitesimals. So this makes it clearer that we're talking about a slope, a rise over run, delta y over delta x. And this can be useful because this tells you what the units of the derivative are. And so if someone hands you, like in 5 or 10 minutes, a weird problem, and you're like, I don't know what the derivative means, one way to start thinking about it is to just think about the units here. So the derivative will have units of y divided by units of x. That can sometimes be a clue. I realized that I wanted to mention 1 or 2 things about homework, and then I'll give you some problems and we'll stop talking. So homework 3 is graded and in mailboxes. People are doing really well. A couple of reminders to write out the question. So don't just sort of like give a solution out of nowhere. Copy over the question as well. And there are at least 2 sort of distinct reasons for that. One is, as I've said, I think the act of actually writing the question helps you focus on what the question is and makes whatever understanding you're thought to acquire as you're doing that problem, it kind of helps it sink in a little bit. And also, when you're looking at your homework like you might on a midterm, it actually can be kind of nice to have like it be self-contained, not just like, oh, 6. Wait, what was the question? And then you have to go over here to your book and look at that. And that's particularly true, and I should have said this probably on the assignment, but for the problems where you're doing graphical ones, like say, here's a function, now sketch its derivative, it's really nice to have the function and its derivative on the same page. And the way, you'll see me, I always do this on the board, or try to have the derivative the function right on top of the derivative, and you can just line up the x values. So I would take the time to write out the function in addition to sketching the derivative, because then you can just see them right next to each other, and it kind of gets in your brain. So one more thought about homework and sort of how to make the sort of learning and understanding you've done stick more. So I would sometimes, and I know some people do this, rewrite the assignment once I'm done with it. And it depends on like what mode I'm in when I'm working on the assignment. Sometimes like I don't know what I'm doing, but I'm sort of excited, or maybe I've had too much caffeine, or I'm impatient, and I'm sort of jumping around and trying things and this and that, and then, oh, I finally get it. And that's a good time then to, maybe if your work was kind of all over the place, to go back and rewrite the problem, which again sounds like maybe an incredibly onerous thing, but even the longest assignments aren't going to take you that long. I mean, not just like copy over blindly, but if you kind of have somewhat scattered notes, taking a little bit of time to sort of collect those notes, neaten some things up. Again, it sort of depends how people work. Some people work in a more organized fashion than me when you're working, and maybe then that's less important. But anyway, something to think about. So a recommendation, not a requirement. And again, people work in really different ways. All right. So 2.4 is about interpreting derivatives, and really all of Chapter 2 is about the derivative and what is it, different ways of thinking about it and picturing it. Chapter 3, Epoch 3, will learn slick ways of calculating it. So let's do these problems. I want to get through all of them. We may pause and confer before then, but let's just go for it. So this is a much more lively discussion than normal, and I don't know how to interpret that, but we'll just see where this leads. So lots to talk about for these. So there are a lot of ways to do this one. What's sort of a quick, common sense way to do this? 30 minus 3. And how did you get 3? So you're losing 1.5 a day for 2 days. You lose 3. You started with 30. You're going to end up with 27. So that's the common sense way, and a perfectly good way to do it. And so, all right. So the reason I wanted, so let me mention some other ways, sort of, to think about this. So you could use this formula, and the point isn't to say, oh, you should have used this formula, but to say, oh, this formula, I don't know, if I can convince you that this is common sense, I mean, like, just, you're losing 3, 27.
Why you're timing it like to from 50 to 50?
Because you're losing this amount per day.
Oh, okay.
Yep. Yeah, so like you have $30, you're losing $1.50 a day for 2 days. Yeah. So if this feels intuitive to you, or like, oh, that sort of makes sense, I want to convince you that this makes sense, because actually you just use this without knowing it. So this is a way to try to get you to feel happier about this. Maybe you're already maxed out at happiness about this, but if you're not fully happy about this, this should increase your happiness. So f prime at 50 is approximately this. So I just put 50 and 2 in for x and h. And what we want to know is this, 52. So if I just moved this over here, and then I can move this piece over here, and I'm going to get f of 50 plus 2 times f prime of 50 is f of 52. So this is exactly what that intuitive thing was. Oh, well, it's how much I have, and then I need to add to that the rate of change, in this case minus 1.5 per day, or per whatever, by the time interval, and I get the new value. And then I heard another group say, well, I'm just going to pretend this is a line. And that's exactly what this formula does. It just pretends something is a line and calculates its slope. This is just the formula for a slope of a line. So all calculus, I mean, not all of calculus, but at least half of calculus, just pretending things that are lines. And as I let this thing get smaller and smaller, the pretend is less pretend, and then you see where that leads you, and it leads to something that turns out to really not be pretend at all. So anyway, the point is not that you should have used all this machinery to do this quick problem, but that the intuition you were using in doing this quick problem is what all these difference quotients are doing for you. OK, so hopefully the happiness level about difference quotients went up a little bit. Are there questions on that one? OK. So let's see. So now we get to talk about pizza. It's probably a good thing it's after lunch, because if it was before lunch, we'll all get too hungry to pay attention after this. OK, so what is the meaning? So f of x is the area of the pizza with radius x. So, or r, you could use r instead of x. So f of 5, what does that tell you? Yep, so it's the area when the radius is 5. Yep. And what about this? Yep, so this would tell you the radius you would need to make a 200 square centimeter pizza. OK, so now this will require a little more cogitation. F prime, 6. It's the rate of change. And what's?
When pizza has a radius of 6.
Yep, so it's a rate of change of the area when we're at, and rate of change with respect to what? The radius. Yeah, so this would have units of centimeters squared per centimeter. I mean, that sort of looks like a weird thing to write, and maybe you really want to simplify it, but I'll urge you to not simplify it. This tells you how much the area increases per centimeter increase of radius. So this would tell you when the radius is 6 meters, 6 meters. It's a big pizza. When the radius is 6 centimeters, if the radius increases, the area will increase at a rate of this many centimeters squared per centimeter. Another way of thinking about this, which is a little less abstract, is imagine we're stepping from 6 to 7 centimeters for the pizza radius. Then we have an increase of 1 centimeter. So then this tells you the additional area you get if your pizza is at 6 centimeters and you increase it to 7 centimeters. So it's the additional pizza you get in centimeters squared if the radius is 6 and it moves to 7. OK, ways of thinking about why this is true? Probably lots of different. And you can answer on like a culinary level, on a geometric level, algebra level. Yeah.
Because we know that the rate of change is x exponential. So this area is pi r squared. So
Yes. The only thing I would say is technically it's not an exponential change. It's a power law change, but all your logic is correct. So it's another way of saying it's curving upward is probably what you meant by exponential. And so it's curving upward, so it's getting steeper and steeper. The little increase gets squared. It's another way of saying it. I mean, I guess you could also draw. All right, so there's 5 centimeters. There's 6 centimeters. 7 centimeters. So like if you're at 5 and you go to 6, you get all this bonus pizza. If you're at 6 and you go to 7, you get all this. And you can see that that circle has more area than that. Anyway, so there are lots of different ways of seeing this depending on, again, how you want to form that argument. OK, I think that's the end of the pizza. OK. So this one will require probably further cogitation. So G of V is the fuel efficiency in miles per gallon of a car traveling at V miles per hour. So we want to turn this, figure out what this means. So a place to start might be to think in terms of units. G is fuel efficiency, so that's miles per gallon. V is velocity, so that's miles per hour. So whatever this is has units of miles per gallon per miles per hour. So does anybody want to take a stab at this? It's sort of a mouthful to fit into one sentence, but I'm going to try.
For every 0.54 miles per hour you're driving at, you burn a gallon.
I think you're maybe you're describing the function and not the derivative. So the derivative is saying how the miles per gallon change. The argument to this is going to be, this is miles per gallon. So this is miles per hour. Sorry. OK, so we can start here. Like when you're going at 55 miles per hour. So then this prime says what happens if you increase your speed. Just like this says what happens if you increase your radius from 5 to 6. It's the additional whatever when you increase the inside by 1. So this would say if you're at 55 miles per hour and you go 1 mile per hour faster, your miles per gallon decreases by 0.54. Should I say that again? OK. So when you're going at 55 miles per hour, if you increase by 1 mile per hour, your miles per gallon would decrease by 0.54 miles per gallon. Should I keep saying that? Yeah, this one is tricky. I need to make sure I sort of talk myself through it before I come to teach it. Like some of these other ones I can sort of think about on the fly. This one it's helpful to have like thought about before class. Partly it's just sort of a long mouthful. You get miles per gallon per miles per hour. But I think this example illustrates how helpful it is to use this notation and think about units. I mean, it doesn't make it an easy problem, but it makes it, I think, a lot less difficult than just trying to decipher that using that prime. OK, so we have one more, which is these things. So now we're talking about the cost of educating 350 COA students, which is about how many we have now. OK, I guess I sort of just said this. This is sort of right. This is the cost of educating 350 COA students. How would you think about what this would be?
Would that be changing cost at the cost of, like, for one more person?
Yeah, so this would be the how much more it would, if you're at 350 students already, how much more it costs to estimate one more person. To estimate one person, to educate one more person. Just like if you're at 6 already, this is how much more area you get if you have 1 more centimeter of radius. So the thing to know, okay, so this is, so the units of this are going to be dollars per student. And it's important to note that this would not be the same as taking the entire COA budget and dividing it by 350. So this is dollars per student, but it's not the average cost per student. And so here's a way to think about this. How much, if we add 1 more person to this calculus class, how much more does it cost the school?
Like it's a marginal.
Marginal, yep. So what would your guess be? Add 1 more person to this class.
Well, it depends on the quantity. So the beginning it's gonna not cost much, but if it's increased too much, then you have to enlarge like the room and like hire a new teacher.
Yeah. But so between 1 and, I don't know, probably 50 to 60 students. I don't know how many people fit in this room. But actually now you can watch it online, so heck, we could have even more. The marginal cost, what I'm trying to suggest is the marginal cost to the college would be almost nothing. Right, because I'm not paid by the hour. Teresa, Corey, and Mackenzie are paid by the hour. So it'd be they'll have to work a little bit more, maybe. If the person came to help hours, they'll have to work more. If they didn't come to help hours, there'll be a little bit more grading. But very, very small compared to the cost of paying me and, I don't know, running the lights and running the camera and all that sort of stuff. So this, as Margarita mentioned, is called the marginal cost. It's like at the margin, at the edge, the cost of 1 additional student, which is different than the average cost per student. And so you can see why it might be tempting from the college's point of view, or if you're trying to manage a budget, to just add a few more students. Like just add a few more students, a little bit more tuition, and we don't really have to pay anybody else anymore. Of course, eventually you reach sort of breaking points. People, you have to build more seats, or faculty members go crazy or something like that. But anyway, marginal costs are different than average costs. All right. Any questions on these? Yeah.
What would the average look like in relation to this?
Okay. So this will be, let's call n the number of students. This would be C. So the slope of this is the marginal cost, and the average cost, I did not expect it to make that sound. So slope is marginal cost so the slope of this line is C over N. And so you can see just in this graphical construction, and economists love graphs like this. If you go into one of, like any class of Davis's, the board will be festooned with graphs like this, and then different colored lines that have different values of the slope. That's sort of all there is to economics. To neoclassical economics, yeah.
What is C350 be the total cost?
Yes, that's the
Not the average cost.
right. To get the average cost, you have to divide by n. Yeah, and that's what doing the slope of this. Slope is rise over run. Rise is c, and the run is n. Yeah, so it's the slope that's the average cost, and you're right, c is the total cost. Yeah. And this actually probably should be a little bit more complicated because there should be some fixed costs, like some costs you have to pay even if you don't have any students. But that's sort of not, I mean, calculus, I don't know, like if you want to have a marine studies program, like you need to buy a boat, and even you have a note, and so like that, you have to incur that cost before you even get any students. Calculus, you need to buy like a blackboard. So math is pretty cheap. But this line might not go through the origin, but that economists and financiers can worry about that. So anyway, this helps to underscore that it's the rate of change at 350, which isn't the average rate of change, and you're always thinking about the additional. It's the additional cost, it's the additional area, it's the additional, or in this case, the decrease in miles per hour. OK, so let's shift now into chapter 2.5, which is the last chapter. And some of you have seen this coming. So we've learned, every day I seem to write it on this board, that derivative is like the rate of change, it's the slope, and it's a function. The derivative is itself a function. It depends on x. You get different slopes for different x values. So wait a minute, why don't we take the derivative of that and we'll call it the second derivative? Yeah, I know. That never goes over well. So 2.5, the second. Rate of change of rate of. Okay. Yep, you can take as many derivatives as one wants. So we'll see. I'll try to convince you today that there are a lot of uses to the second derivative, and it turns out that there are very few uses for third and higher derivatives. So physics, so the second derivative, it's a rate of change of the rate of change. So the rate of change is position, going back to the running cat. The rate of change of velocity is acceleration. And surely at some point, you've encountered Newton's second law, F equals ma. So that's acceleration, that's a second derivative. And so sort of all of physics deals with second derivatives, almost never third derivatives. Very rarely. There are a few equations I've seen with fourth derivatives, but that's sort of it. So there's not a chapter like 2.6, 2.7, 2.8, 2.9 that's a third, fourth, fifth, sixth derivative. So we sort of stop at the second. And it's sort of just what you think it is. It's the rate of change of the rate of change. And if you can get over the fact that that sounds silly and circular, it's not so bad. So let me say one, I think just a little bit of geometry, and then we'll probably spend the rest of the class talking through a bunch of examples. So what else? Is there anything else I want to say about this? Oh, I guess I should mention, just so I don't forget to later, so using that other notation, it would be something like that. I think I'll mostly use this, which you'll read as like f double prime.
Is it done on purpose that the square this first one is d and then on the second?
Yes, because I sort of think of it as so like this is like an operator, like a command. It says take two derivatives of y. So yeah, so that looks like a weird thing. I mean, maybe it is a weird thing, but it's a thing. All right, let's see here. All right, there is f of x for something. Where is f of x positive? when it's people are just sort of tilting this. It's over there. Yeah, yeah. So for this half, f. Oh, I might have did I say f of x? I meant to say f prime of x. I might have misspoken. Okay. So who knows? Okay, we have no idea where f of x is positive. So those of you who are staring blankly at me were 100% correct. And those who answered over this way were correctly reading my mind. I meant to say f prime. So everybody was right. So f prime of x is positive here. So remember, positive first derivative means the function is increasing. And negative means the function is decreasing. So the function is decreasing right over here. OK. So now let's think about what's happening to the derivative. So here the derivative is positive. Here it's steeper. There's more positive. So the derivative is changing how? Yeah, it's increasing. Derivative is getting bigger. So that means the second derivative is positive here. So f double prime is greater than 0 because f prime is increasing. The rate of change of the rate of change is positive. OK, so let's think about what's going on over here. You're losing a lot of money. Here you're losing less money. How would you feel about that change? Less bad, which would be better. It's a positive change. So your rate is negative, but the rate of change of the rate of change is positive. So f double prime is positive here as well. I should make it a little clearer.
Repeat the thing about the double. Why is it?
So slope is a large negative number. You're losing a lot of money per day. Slope is a less large negative number. So this might be -4, and this might be -2. So that's a positive change, because -2 is bigger than -4. So everywhere along this curve, the second derivative is positive, even though the first derivative changed its sign.
Could you repeat that a couple of times?
So everywhere along this curve, the second derivative is positive because the slope is always increasing, even though the function itself is decreasing and then increasing. I thought I just did draw in a picture. like sketch f prime? Ah, OK, yeah, that's a good idea. So this might be f prime. And then what would the derivative of this look like? Yep. OK, yep. So the slope starts negative, increases, becomes positive. The slope is increasing all the time, so the second derivative is always positive. Let's do one more thing. So here's another thing. Maybe we'll do the graph one right away. That's better than me saying the rate of change of the rate of change is the change at the rate which is changing. All right. So what would a graph of, all right, so this is f. We want to do f prime. What's that going to look like? Yeah, it starts positive, goes to 0, gets negative. It's going to look something like that. So then what's the derivative of this line? Yep. So derivative goes from positive to negative, but the second derivative is always negative. And so what the second derivative tells us geometrically is the concavity. This is concave up, always bending up. This is concave down. And so a positive second derivative means it's concave up. Negative means it's concave down. But I would encourage you to not memorize that, and just know that the second derivative is a derivative of the derivative, and derivatives are rates of change. So you can always talk yourself through this. And I know the language and the words seem a little weird, but you'll get used to it pretty quick. All right, so I think we should just launch into some examples. The algebra of calculating a second derivative, it's just you just do it twice. You calculate a derivative, you say that was fun, I'm going to do it again. So there's no more complications there. It's just how to think about it geometrically and sort of conceptually. So we're going to do probably not any algebra, but more of these what do things mean and drawing pictures and so on. So let me hand these out, and I think, because I want to make sure to get to the next sheet, I might not have you do all of the problems on this. But let me hand it out, and then I'll let you know. All right, let's talk through these. Particularly number 3 with the falling rain is a little bit tricky. But first, let's do 1 and 2. So Laura, this is actually a real example. I think it was the first time I taught calculus here. Laura Casey was sick for a good part of the term, and this would be often how we would ask her how she was doing and express the answers in terms of various derivatives. It was also, maybe it was more apparent because I was teaching in the Strauss room, which wasn't called the Strauss room then, and didn't have those humongous tables, so like more than 12 people could fit in the room. And it's one of these things where it was, I think I was teaching in winter term, and so there was some sort of horrible COA cold going around, and every day people would plop down and like take out boxes of Kleenex. Anyway, so sickness was a very recurring theme in that first calculus class. So anyway, I'm feeling bad today. Presumably that's a negative thing. Feeling better than yesterday, so that means that this would be increasing, and then this would be and getting better faster and faster. If you were to sketch this, which you weren't asked to do, it might be something like that. So you're still under the weather, but you're getting better, and the amount by which you're getting better is getting larger. Defense budget will increase, so that B for budget. But the increase will be less than it was the year before, so that would be a negative sort of thing. So yeah, so there are lots of different ways to take in, things that could be bad and make them sound good by talking about the second derivative instead of the first.
How would you graph that?
Maybe something like that. Yep. All right. So let's talk through the rainfall problem. And here, for me, the key, I would say the key to not getting confused. That's not true. The key to making it less likely you'll get confused is to, I think in terms of units. So I find units really helpful for this problem. I find units helpful in general, but particularly for this one. So f of t is a number of inches of rain that have fallen after t hours. So f of 10 is 1.4. The output for the regular function is inches. The input is hours. So this would say after 10 hours, 1.4 inches have fallen. OK, so now the derivative of that, we call the number of inches that's fallen y. I thought about calling it h, but h might have bad for like height of rain, but h might have bad connotations for you now. We'll stick with y. So that would be inches, right? dy dt, that would be inches per hour. So this statement would mean that after 1 hour, so 1 a.m., 1 hour after midnight, the rain is falling at 0.1 inches per hour.
Can you see?
Yep. So after 1 hour, the rain is falling, or the water level in your rain gauge is increasing at a rate of 0.1 inches per hour. Oops. I lost a prime here. All right. So F, I lost a prime here too. F double prime is the rate of change of the rate of change. The rate of change is inches per hour. And so we want to know how are inches of hour changing per hour. Rate of change of rate of change. So this would be like acceleration. So this says, after 10 hours, the rate of rainfall is decreasing at 0.2 inches per hour per hour. So I'm just, not in any sort of mean way, but I'm enjoying the looks of contempt, dismay that everybody's sending towards me. Sorry, I'm sort of savoring that for a moment. All right, so let me. So this means that the rain is slowing down. The storm is lessening. How much is it lessening? Well, the rate of rainfall is decreasing at 2 inches per hour every hour. All right, let's see. People are scowling a little bit less. So I mean, these are confusing. These are not intended to be easy sorts of things that you should just be able to figure out. You have to sort of talk your way through them. Use units as a guide. All right, so the inverse function, we swap around input and output. So now, instead of having the output be inches, the input is inches. So this would say, like, after 1 inch has fallen, 3 hours have passed. That wasn't the best grammar, but the math was OK. It takes, in 3 hours, 1 inch has fallen. You can sort of read the sentence left to right or right to left. OK, so now the one you've all been waiting for. If the output has units of hours, the input has units of inches, the derivative of that is going to have units of hours per inch. It's backwards. It's the other way around. So instead of inches per hour, it's hours per inch. The input to the inverse function is still inches. So this says after 1.4 inches have fallen, rain is falling at a rate of 3 hours per inch. It would take 3 hours for 1 inch of rain to fall. Is another way to say that. Right? I mean, you could describe speed in terms of miles per hour or hours per mile. Or like when you ask somebody how fast they run, they might say, "Oh, I run a 10-minute mile," instead of whatever it is, instead of miles per minute or miles per hour. Anyway, so this is sort of like upside down speed. But anyway, it's 3 hours for the next inch to fall. So these are tricky, but hopefully fun tricky. All right. Maybe not, I don't know. But the point is, like, this is hard. I don't think these are easy problems. All right, so a bunch of words. Now we get to do stuff in pictures, and let's see how people feel about that. So let's talk through number 6, and then this is perfect. Then 2 more graphs to work on. All right, so this is a graph of f primed. So f double prime is the derivative of this. To go from f prime to f double prime, a single to a double derivative, you just take a derivative. So let's see, where is the derivative of this function positive? It's positive at 2. It's positive in this entire region there. So in this region here, the function is increasing. In this case, the function is f prime. An increasing function means a positive derivative. So it's the same story as before. It's just now the thing that's increasing happens to be a derivative. OK. So now let's think not about f double prime, but about f. So now you're handed f prime, and you want to know when is the function f increasing. So the function f is increasing when f prime is positive, yep. And that would be in this region and in that region. So these are actually the same question. Wherever f is increasing, f prime is positive. Wherever f prime is positive, f is increasing. And then the negatives are the opposite, or the would be here. Let's see. I'm going to guess that you simultaneously feel not 100% comfortable with this, but that you don't want to ask a question about this one, because this one is what it is now, and we should do some more graphs. That's what I was planning on doing. Hopefully that's OK with you guys. So let's do some more graphs, because I think you need to do a bunch of these. We'll do some more graphs, and then we'll talk about them. So do both of the problems here. There's one problem on the back, one on the front, more to puzzle through. And
Oh, is it the same one?
so we've got around 7 or 8 minutes by my machine, so let's talk through these. So this is a graph of f prime, and this is what you have on your sheet, but a less nice version. This is 1, this is 2, and I should look at the nicer version. So which is larger, f prime of 1 or f prime of 2? They're the same, so I guess circle them both. F double prime. F double prime is a slope of f prime. So this is asking where is a slope larger, at 1 or at 2? 1, yep. Because the slope, it's going up here, the slope's positive. Here the slope's negative. So here's a tricky one. Where is the function itself larger, at 1 or at 2? Why do people say 1? What's an argument for 1? Or is there an argument for 2? We could say, OK, 2. All right. That's the OK, yeah. So the derivative is positive for this up until here. If the derivative is positive, what do you know about the function? Increasing. If the function is increasing, which will be larger, f1 or f2? 2, yeah. Good. OK. OK, so now f2, f prime 2 and f prime 4, which is larger, so 2, 4. It's larger, but it's negatively large. Oh, no, sorry, f2, sorry, we're reading off the graph. So f prime 2 is larger, because this is just higher up than there. And then f double prime 2, that's asking about the slope of this. Is the slope larger at 2 or at 4? But it's more negative, so the slope is less negative here. Sorry, I started answering problem 5 when I was asking about problem 4. So that's a bigger negative is actually smaller. I mean, it's annoying, but that's the way the world is. OK, so last one. Now we're back to a function of f, the function itself, and we want to think about these 3 things. So where is the function itself positive? Yep, in these where it's above the axis. The derivative is positive when the function is increasing. And that looks to me like that would be from here to here and from here to here. Then f double prime is positive. So I would say, well, so in this region, is f double prime Positive or negative? We're in here. It's going to be negative because you have a positive slope. The slope becomes less positive, more negative, more negative. So all in this region, this is a negative second derivative. Over here, the second derivative is positive. You've got a negative slope. It's less negative. That's a good thing. It's 0. That's good if it used to be negative. Then it's more positive, more positive. So all in this region, the second derivative is positive. In this region, it's negative. And it probably changes over somewhere, like somewhere in the middle here. So this f double prime is negative. F double prime is positive. So if one stands back a little bit, the function is concave down here, and then concave up here. Where concavity changes is called an inflection point. Does that? Trying to think of some grand concluding remarks to make. So second derivatives are merely the derivative of the derivative. And as long as you don't sort of get yourself tied up in tongue twisters, and I think you should talk yourself through these, rate of change or the rate of change, you know how to do all these. But they're a little tricky, particularly some of these interpretations, so you'll practice a bunch, and we'll continue to revisit these even in the third epoch of the course, which will begin on Monday. So have a great weekend, and we'll see you then.